Hello and welcome back to Calculus 1 section 3.8 on implicit differentiation. We need to talk about derivatives of relations that are not functions, because those are still curves and they still have tangent lines, and those tangent lines still have slopes. Therefore, there has to be a way to find the derivative somehow, because the derivative exists because the slope exists, right? So if we take some kind of a curve, let's take an S, for instance. That's not a function because it fails vertical line test, right? No matter where you make it into a dollar sign, it failed the vertical line test. So it's not a function. However, I can find the tangent line at this point. I can find the tangent line at this point here, right? There is a horizontal tangency right here. So there are tangent lines all over the place, and every single tangent line has the slope m, which came from the derivative. So there has to be a way to take the derivative of these expressions that are not functions. So how do we do that? Well, we are going to use the chain rule. But before we go into that, let's talk about implicit and explicit form to write a function or to write an expression. So far in mathematics, you are used to y equals f of x. This is known as explicit form. Y alone on the left, everything else on the right. That's your standard y equals x squared plus 3, y equals 3 ln x, y equals sine squared of whatever. So all of the functions you have ever dealt with so far, they were all written this way because you can always have y equals f of x. But then you also have met some of these curves that you cannot write as y equals everything else. And then when you graph them using either the software or point by point calculation, you realize that these particular functions, these particular lines are not functions. They fail vertical line test. Therefore, they cannot be written as y equal f of x because they are not f of x to begin with. So how do we describe those in mathematics? The perfect example for that one would be a circle, right? Practiced drawing circle for years, so those are the mad skills, as you can see. Here's a circle. And for this circle, we have, let's put this on some coordinate system, x, y, and say that the radius is 3. So what would be the equation for this circle? Anyone? This is like the basic algebra thingy. X squared plus y squared equal to 9. That needs to be instant response, especially that you had circles in pre-calc 2 with trig. You cannot write this as y equal everything else because you will have a plus and minus in there. Right? If you try to solve this, the y squared is 9 minus x squared, and you take square roots, you get plus minus square root of 9 minus x squared. See, uniqueness is ruined. It's no longer it's no longer unique. If you studied the definition of a function before, what did you learn, right? For every x in the domain, there is a unique y in the range. So pick a unique x in a domain over here. Let's say you pick number 2, x equals 2. How much is that? It's going to be plus minus root 5. That's 2 y's associated with single x. And that's a no-no for functions, right? So it's not a function. And because it's not a function, right, we cannot use the derivative in the form that we are used to. But we still know there is a vertical tangency there, there is a horizontal tangency there, there is this, there are tangent lines everywhere. So we know that it's differentiable, but we have to figure out how. So now to write that, we have the explicit form of x and y's equals to 0. So now this equation can be written in this form, where you would say, now this form will be used a lot in Calculus 3. You would say f of xy is equal to x squared plus y squared minus 9 equal to 0. So you can see that this is equal to 0, and in between you have what we call now implicit way to write these expressions. This is where x's and y's are on the pile. We do not separate y on one side and x's on the other because we can't. And in some cases, right, we have to do that. Now, the truth is that all of the functions can be represented this way, even the ones that are functions, like y equal x squared minus 1. That's a function, right? It's a parabola. It passes vertical line test everywhere. So that's a cool, right? You can still write it as f of xy equals to y minus x squared plus 1 equals 0. There it is. You can still write it in implicit form. So implicit form is not just for expressions that are not functions. They're actually for everything, where the function notation only works for functions. So we are studying this implicit form, and now we can take the derivative of the implicit form. And the rule is you are taking derivatives the regular way, but every time when you take the derivative of y in respect to x, you have to follow with a chain, because we are assuming that y is the function of x, therefore the chain rule has to kick in. So we are going to take the derivative of our implicit form and take the derivatives of x terms the way we always did in the past. But for the y terms, we have to follow with the chain. Now, I'm going to expand on it later, but for now, it's good enough. What does that mean if we are to take the derivative of our circle equation? It's okay. You don't have to, equal it to 0. You can equal it still to 9 and then just go term by term. Focus on the derivative of x squared. That's just 2x. There's nothing there, right? And then the derivative of y squared. Well, this is where the chain rule is going to kick in. So we have plus 2y, and here is the dy dx that you have to write in as a chain rule, because you took the derivative of y in respect to x. X is your main variable, and then the y is the independent variable, but then they are linked through that function, so we have the chain rule piece in there. And finally, the derivative of 9 is 0. So now all I need to do is to do the algebra here to um, solve for dy dx, because I'm looking for a derivative, right? So 2y dy dx is equal to negative 2x, and when I divide y and cancel the 2's, I get negative x over y. This is the derivative of a circle. And for the first time, your derivative contains y as well. And if I want to find the derivative at some point on the circumference of that circle, I have to provide you with x and y. Right? Before, for tangent line, you just needed x, because you can use the function to find y. But now, right, you need to be provided with x and y to plug them in to get the slope m. So if we carefully look at the circle, this point over here is 3, 0. We are expecting a vertical tangency. We are expecting infinite slope because it's a vertical line. So the slope is negative x divided by y, which is 0. Ooh, right? There is your 3 divided by 0. Slope does not exist. It's infinity, right? So that works. How about my horizontal tangency over here going through, let's say, 0, negative 3? Well, for horizontal line, we know that it should be 0 slope. So slope is 0 divided by negative 3. Why did I put negative? Yeah. And the negative goes away, and we get a 0, right? So horizontal line. Horizontal line, because the slope is 0. So, going back to our problem, the reason why we want to find the derivative of circle equation is because we want to find tangent lines around circle. Now, if you're interested in why would we actually bother with that at all? Well, if you ever took an object that is connected to a string and, you know, above your head, like made a circle with it, right, as you were rotating your hand, so it looked like a helicopter, right, blades. If you look at that motion from the top, so you have some object attached to a string. When you start rotating that, it's going to create a circle, and the string is going to be straight, right, under tension, and this is where you hold the string in the middle, and then it's going to spin around. The tangent line that this has at every point on the circumference is going to be the vector of the velocity. If you let go of the rope, the object will go in a tangential, right, in the direction of the tangent line. So problem like this is very important, right, to understand, because the motion will work that way in the physical reality. So if you let go or the rope snaps, the object, even though it was going in circles before while the rope was there, the object will go this way. It helps you also understand why planet Earth stays in the orbit around the sun, because you have the speed at which planet, I don't need the new picture, it's the same picture. It's a little bit different because it's elliptical and the sun is in the focal point, but you know, if you look from far away, you can call it a circle, and it's not, but call it. And you will have the gravitational attraction to behave as a rope, and you can see that the motion, the velocity of the planet wants to go out, but the gravitation of the sun pulls the object in. So the Earth ends up always falling at every tangential point. The Earth's overall vector ends up falling. So as much as the speed wants to go tangentially out and away from the sun, the gravitational pull between Earth and the sun pulls it back in, and it just ends up being this, I don't want to say never-ending because it's not never-ending, but say never-ending circular motion. So the Earth wants to go this way because it's moving at the very fast velocity, but then the gravitation pulls it back and it keeps bending and bending and bending. So Earth is infinitely not infinitely. There is an expiration date to a planet, right? Eventually it will be done, but we don't have to worry about it for 5 billion years. So it keeps the orbit around. And clearly you can go ahead and figure out what would be, if you want to use the coordinate system, right? What would be the ellipse? That's not that hard, right? Because ellipse has the x squared over a squared plus y squared over b squared equals 1. These are just constants. The derivative is pretty much the same. You can figure out what these are in lengths. Go research it online. You have what the orbit of Earth is around the sun in terms of the ellipse, because it is elliptical orbit with the sun being in one of the focal points. That's the center, 2 focal points, and sun is in one of them, and Earth goes around. You can find the velocity vector as the Earth goes around. Now, these concepts sound crazy, right? But they are crazy simple when you know and understand the basics of what we are dealing with today. So now we were able to use the implicit differentiation to come up with this derivative of the circle. How about 4y to the 6 is equal to 9x squared plus x minus 3. How about the derivative of this? Take the derivative of the entire equation, not a function. You have y to the 6. This thing is going to do some things like this and it's going to fail. We again do it term by term, and every time we take the derivative of y, we have to follow with the chain dy dx. So 4 times 6 y to the 5, and because I took the derivative of y, I have to follow with dy dx with the chain, equal to 18x plus 1. All I need to do is to get rid of this mess, and dy dx is alone. So dy dx is equal to 18x plus 1 divided by 24y to the 5. We're done. That's it. That's the derivative. Now, if you need to do something with that derivative, you go ahead and do it. It's, solve the equation to figure out min and max and stuff like that, or go into the slopes and figure out the tangent lines so you can figure out tangential motion and so on. There's a lot of stuff you can do with this. The main concept now for our section is to learn how to take this derivative, and then later on in application, you'll see what we can use the derivative for. I already gave you a couple of examples, but sine xy is equal to y cubed minus 1. There's a winner. Right there. What do you think we could do now, or should do now? This is not a nice problem. Can anyone give me any idea? Okay, the YouTube says if we can make the y cubed alone, you can, but it's not gonna help anything because you still have another y buried within sine. So the answer is yes, but no. There's no reason for it.
Could you take the inverse sign?
That is also gonna make it worse. Guys, this is exactly what we want to discuss, right? What are all of these things that need to happen here? This is going to be product rule inside the chain rule, worrying about implicit differentiation along the way. We are going to take the derivative from each term as we see it, just like we did when it was just x around, but now we have the added annoyance, let me put it that way, of every time we take the derivative of y, of any kind of y, we have to use the chain rule dy dx. Derivative of sine is cosine, and we copy the guts, times the derivative of xy. The derivative of xy is product rule, so copy the first, derivative of the second, and then dy dx. Because remember, this is a y. When I take derivative of y, you get 1. And then I have to follow with the chain rule. So that's the derivative of the second. Plus copy the second, derivative of x is 1. We don't put the chain rule there. Equals 3y squared dy dx minus 0. Now we simplify this. It's going to be x cosine xy dy dx plus y cosine xy, when I distribute, is equal to 3y squared dy dx. A lot of mess, but I had over here, let me write that in blood, product inside chain rule, and then on top of that, we have to worry about, oh, I took the derivative of y, follow with the chain dy dx. So one more time, derivative of sine is cosine, and we copy the same argument. And then, because this was not just cosine x, it was cosine xy, I have to take the derivative of this as a chain, which is the parenthesis. Happened to be a product rule. Copy the first, derivative of the second, plus copy the second, derivative of the first. Right hand side, just derivative of y cubed is 3y squared, and because I was taking the derivative of y, I am following with the chain rule there. And now all I need to do is to make this dy dx equal everything else. For that, we move dy dx terms on the one side, and all of the terms without dy dx, shift them to the other side. So I have x cosine xy dy dx. I am bringing over negative 3y squared dy dx, and I am shipping off to the other side negative y cosine xy. Can anyone tell me what was the reason to put them on the same side?
So you can factor out
Beautiful.
dy dx.
Excellent. We factor out dy dx. It leaves this other mess in parentheses. And all I need to do is to divide by this to get rid of it. So divide both sides by this parenthesis. And what you get is dy dx is equal to negative y cosine xy divided by x cosine xy minus 3y squared. This is where the story for most of you ends, unless you are a computer science major. If you are a computer science major, you need to simplify this more, because we can reduce the amount of computations that the computer needs to do by simplifying this algebra further. So I have to make that clear that your software will be better and faster if your equations that are there in the software are the simplest possible. So now this flex in blue is for computer science folks. What do you have to do? First, you eliminate this minus simply by multiplying that minus in denominator, and what that does is it switches the order of this. You are already one calculation down because computer doesn't need to compute that negative anymore. So this one already, if you have to do 10,000 calculations of this one over here has 10,000 calculations less to do, because there are those 10,000 minus signs are not present on the right hand side. And then another flex over here would be to divide top and bottom by cosine xy. Again, this is computer science only, and those of you who care. So now look at your numerator. It's just y, because the denominators cancel, right? Over here, you are going to get 3y squared over cosine xy minus x. Now you would say, well, I just added this division and blah, blah, blah. But you can write cosine as a secant on top. So y, and you have your 3y squared secant xy minus x. This has a lot less calculations than that. So I have to make it clear to the computer science people that this is something that you are looking for all of the time in mathematics, to get used to it, so that when you write your software, it's efficient later on because it has less calculations to do. Every time you have to do 10,000 calculations or something, and you heard that's what the word optimizing means, right? Figure out what are your mathematical formulas and functions and so on, so that the computer has the least amount of calculations to do. And trust me, on million calculations, right, in video graphics processing and all that stuff, it's a huge saving, and that's why you get to be paid a pretty bucks, because you see how to go from here to there. You see that this is not simplified and you can make it better. So that's your true computer science right there, if you want to use these things properly. Let's pick an example from the textbook for our implicit differentiation. Problem 36 looks diabolical enough. xy plus 1 raised to the third power is equal to x minus y squared plus 8. So they want the derivative of that. All right, I'll give you some time. No, this is not easy. I hope we all see product rule inside the chain, and then you also have to worry about derivatives of y. So if you don't have the product rule, it's immediately no bueno, right? You have to have that product rule going. All right, let's take a look at this one together. And then after this, we just need to do the second derivative and call it a day. So I have a chain rule. That's going to be 3 blah squared. And the blah is xy plus 1, right? Then I need to do the derivative of the inside as a chain, and that's the product rule. So copy the first, derivative of the second, plus copy the second, derivative of the first. Equals, derivative of x is 1, minus 2y dy dx, plus 0 for 8. And now we need to clean this up. So what do I have? We have this times this one and times y. So 3xy plus 1 squared, 3x, sorry, 3x, there's an x here. And we usually put dy dx at the end, plus 3y xy plus 1 squared. So this y is this y here, and this x is this x in there. We just distribute it. That's basic algebra. Equal to 1 minus 2y dy dx. Now, remember, keep the terms with dy dx on the left. So we have 3x xy plus 1 squared dy dx. Bring plus 2y dy dx from the right. And then have 1 minus kick 3y xy plus 1 squared to the right, because it doesn't have dy dx. Factor out dy dx and skip a step. 1 minus 3y xy plus 1 squared with 3x xy plus 1 squared plus 2y. Tons of fun, as you can see. But that's your derivative. It's implicit derivative. Now go ahead, go to a graphing utility you like and graph that line, see what it, see what it looks like. Let's, you know what? Let's find one of these tangent lines. We can do higher derivatives also next class. It's not a big deal. Let's do one of the tangent lines and then call it a day. So tangent line at -1, 1. That's the question. For x to the fourth minus x squared y plus y to the fourth equals 1. X to the fourth minus x squared y plus y to the fourth equal 1. Same principle like always before for tangent line. Get the derivative, plug the points to get your slope. So we have to get the derivative of x to the fourth minus x squared y plus y to the fourth equal 1. The derivative is 4x to the 3 minus, and here comes the product rule. Copy the first, derivative of the second, plus copy the second, derivative of the first, plus 4y cubed dy dx equal to 0. Now, you could go and simplify everything, but you could also plug in numbers right away. And then instead of dealing with algebra, you can deal with arithmetic, right, which is computation. So pick your poison. If you want this to be simplified at least a little bit, you can say 4x cubed minus x squared dy dx minus 2xy plus 4y cubed dy dx equals 0. You can do that. But when you are looking for the tangent line, you really don't have to solve it all the way to dy dx equals everything else, because you can plug everything in now. Plug in x equals -1, right? X equals -1, y equals 1, and dy dx equals the slope m. The entire row becomes a computational joke. 4 times -1 cubed minus -1 squared times m minus 2 times -1 times +1 plus 4 times 1 cubed times m equals 0. I just plugged everything in. And from this point on, we just solve this basic equation. -1 cubed is -1, so -4 minus m, right? -1 squared is 1, so that's gone. Plus 2 plus 4m equals 0. This is 3m minus 2 equals 0. M is clearly 2/3. And we also have the point, -1, 1. So now we can plug that into y equal mx plus b and calculate the rest. So that's -2/3, +5/3. So the tangent line at -1, 1 is going to be y equals 2/3 x plus 5/3. Tangent line with basic derivatives, tangent line with limit calculation for the derivative, tangent line with the product rule, quotient rule, chain rule, implicit differentiation. Next class, logarithmic differentiation. For this, we have trigonometric inverse trig coming up as well next class. All of those sections have tangent line problems. The only difference between them is which derivative shortcut formula are you using to come up with the slope. The rest is all the same. You have the slope, you have the point, plug all of those in to get your line. Cheap and easy. I am going to, well, first bye, right? See you next week. And I'm switching to the office hour. If you guys have any questions, follow the link from Canvas. See you there. Bye.